Hi, this is Lalit Vasist and you are watching Engineering Made Easy. This video lecture is about Schottky Diode. Here we will discuss the structure, working and applications of Schottky Diode. Okay. So first of all, let's see its symbol. This is the symbol of Schottky Diode. Look at this. This is the anode side, cathode side, negative terminal. Cathode is the negative terminal, anode is the positive terminal. Okay, and this one is the simple structure of Schottky diode. Look at this. Here is the anode side and here is the cathode side, and this is simple structure, the metal and N type. Okay, it has two sides. First side is the metal side and another one is the N type. Okay, we know that semiconductors are of two types. Impurities, on adding impurities it becomes of two type, N type and P type, but here in this case it only has N side. So electrons are in majority in this side, and metal also we know that are full of free electrons. So both of these sides contain majority charge carriers as electrons. Okay, this Schottky diode is also known as Schottky barrier diode. Okay, and it has a metal. This side is of metal. Generally we use gold metal for this, and here is a N type, as I told you. So it is a metal semiconductor interface. It has metal semiconductor interface. This is N type semiconductor. And as both of sides of this diode have electrons as the majority charge carriers, it is a unipolar device. Unipolar means having only one pole. It do not have P side like a normal semiconductor diode, where we have two terminals, two sides, N type and P type, and P has holes as the majority charge carriers and N has electrons as majority charge carriers. But we have in N type electrons as majority charge carriers, and also inside we have a large number of free electrons as majority charge carriers. So it is a unipolar device. This diode is also known as hot carrier diode because as we forward bias, suppose we forward bias it and this side is positive and this is negative side, here we apply the negative potential. So on forward biasing means N terminal has negative potential. So when it is forward biased, then this terminal anode is at positive terminal, positive side, higher potential, this at lower potential. So the direction of electric field is always from higher potential to lower potential. So electric field is from left to right direction, in this direction. Okay, from here to here. So electrons will face force in opposite direction to the electric field. Okay, here we have electrons and here we have electrons. So what happens, these electrons, the conduction electrons on the N side acquire enough energy to cross the junction and they enter into this metal with high energy. Okay, therefore these are commonly called as hot carriers. As we now know that since there is no P side in this, so there is no depletion region like normal semiconductor diode, where we have a depletion region and one side has N type, one side is of N type and another is of P type, and depletion region in between. Since both of these sides have majority charge carriers as electrons, so depletion region is absent. One most important property, or you can say the advantage of using Schottky diode, is that it can be used at high frequencies. High frequencies, so it works as a on off switch, a high speed or a high frequency on off switch. Okay, so it can be used for the rectification of high frequency signals. We can use it for frequencies higher than 300 megahertz. So this is the main advantage. It finds applications in switching power supplies, nearly 20 gigahertz up to 20 gigahertz, and in also in sensitive communications receivers like in radars because of its low noise figure. And we can also use these Schottky diodes in computer gating and in clipping and clamping circuits. So here we will see how we can use the Schottky diode for the rectification of high frequency signals. Okay, and what is the reason how it is possible. Look at this image here. We have two diagrams. This is for the normal diode. This is the normal diode rectification, and here is the rectification using Schottky diode rectification. What is rectification? Rectification is a simple process where we convert a AC signal into a DC signal. Okay, we cut off the negative waveforms. Okay, so let's see how the how the normal diode is used at low frequency and high frequency, and what is the shape of the waveform that we obtain at the output. What is the problem with the output at high frequencies when we use normal diode for rectification. Look at this. Here we are applying this is the simple normal diode rectification. So we are applying here first V input as low frequency. It is a low frequency signal. Then we will see the same experiment with the high frequency signal for normal diode. So when we apply this low frequency signal to this diode, then we know that this is a AC signal, so it changes the direction of current. So suppose when it is positive for the first cycle, it is positive, and this is the negative side, this is negative, then this diode will conduct, so it will pass this waveform. But for the another cycle, it will have for the another half part, it will have changed polarities, and this part will become positive and this will become negative. The direction of current will change, so it will not allow the current to flow in the reverse direction, so this negative part will be clipped. So this is the thing that we already know in case of rectification of normal diodes by using normal diodes. But when the frequency becomes very high, then it becomes very difficult for the normal diode to cut off, to clip of the negative part. Why it happens, why it takes place, I will show it to you how it takes place, what is the reverse recovery time, how the charge storage takes place at the junction, and what is the reason behind this noise that is appearing in case of high frequency normal diode rectification. But before this, let's see this diagram also, that this is the rectification using Schottky diode. At high frequencies, we are using up to 300 megahertz frequency, which is very high, and this is the diode, Schottky diode's notification symbol, and we are getting very clear rectified output. It has converted this AC high frequency signal into a DC signal, having clearly it has clearly cut off the clipped off the negative part. Okay, so it's time to understand how this takes place, how it is able to allow high frequency rectification high rectification of high frequency signals. Let's see it. So let's try to understand the concept with the help of this simple diode. This is a normal diode. The normal diode takes time to turn off because of charge storage at the junction, which is known as reverse recovery time, TRR. Actually, what happens, we know that this is a simple normal diode, and it is also forward biased. It is forward biased means P terminal at higher potential in comparison to N terminal, and here is the depletion region. So electric field in this case is from higher potential to lower potential. So in this direction, the direction of electric field is in this, from left to right side, and because of this polarity of voltage source, and because of this electric field direction, the electrons having negative charge feel forced in opposite direction, that is F is equals to Q into E. So in the opposite direction of the electric field, while these holes that are positively charged feel force in the direction of the electric field, the same force Q into E in the direction of this. So electrons are moving here and holes are moving in this direction, so both are moving towards each other's side. So we find lots of electrons and holes are collected at the depletion region. So diode starts to conduct, but when we turn off this diode, or you can say when we remove this voltage supply, then it this normal diode takes time to turn off because of the charge storage at the junction. And this time is known as the reverse recovery time. The time that it takes to remove these removal of these charges from this depletion region is known as the reverse recovery time. So it causes some delay. Therefore, these normal diodes cannot work at high frequencies, because at high frequency input signals the direction of current changes very fast. So the charge remains stored at this depletion region. But in case of Schottky diode, one side is metal and another side is of N type. So there is no depletion region. Actually, depletion region is absent here, and the problem was the storage of charge in the depletion region. Since depletion region is absent, so this problem is also not present, because there is no p side for the depletion region to form. Therefore, the depletion layer is absent in it. So no problem of charge storage at the junction. Therefore, the diode can be switched at very high frequencies. That's the reason the reverse recovery time issues or the charge storage issues in the junction are not present in Schottky diode. So friends, did you get the concept? So this was all about the Schottky diode's structure, working and applications. We learned here how it can be used at high frequencies. Okay, so see you in the next video with more such useful videos. And if you liked it, please click on like button and subscribe my channel Engineering Made Easy, and you can share the video with your friends. Thank you for watching. Bye bye, take care. Friends, for more such videos you can subscribe my channel Engineering Made Easy, and please don't forget to like and share the video if you liked it. For more detailed information you can visit my blog. See you soon in the next video. Till then, bye bye.